Hello everyone, today I have a very interesting topic. In a daily life, multitasking is chaos. But in the world of embedded systems, multitasking isn't a headache. It's art, precision, and real-time elegance. Interesting, right? Welcome to Embedded Tea. Let's have a sip of tea made of real-time operating system. So let's start with the OS. Have you ever wondered how and where OS works? Let me show you. Suppose you want to give a task to your CPU, like saying, hey, can you play some music? But the CPU only understands low-level instructions. It has no idea what you're saying. That's where the operating system, or OS, comes in. You write commands in machine-readable code, and the OS handles everything. It's the translator, the bridge, and the master scheduler of all your chaos. Talking to the hardware, managing memory, and making sure your music actually plays. Now let's understand how an operating system really works. Imagine this hierarchy. At the very top, that's you, the user, wants to interact with the hardware like CPU, RAM, and storage disks, and wants to complete the well-defined tasks. Our operating system sitting between you and the hardware, as a manager, as a translator. But here, user doesn't directly interact with OS. User uses system and application programs like compilers, text editors, databases, even Photoshop type of software to interact with OS. You may think, what does the OS actually manage? Well, it takes care of memory, so apps don't stomp on each other. It handles processes, juggling multiple tasks in the background. It keeps track of time for scheduling and delays. It manages your files and I/O devices, so your keyboard, screen, and storage all talk in harmony. So that was an OS. But now let's dive into a special kind of OS, which is RTOS. So, in a world of electronics, there are a variety of OS available based on the end application. Here are those. First, the batch operating system, one of the earliest OS types. It processes groups of jobs together without requiring user input. Then there's the multitasking OS, found in most desktops and smartphones today. It can run several applications at the same time, letting you browse the web, play music, and code, all in parallel. A real-time operating system focuses not just on speed, but determinism. It ensures time-critical tasks are executed within a guaranteed time frame, which is essential for systems like medical devices, robots, and automotive controls. A distributed OS runs across multiple interconnected computers, but presents them as a single system to users. It's commonly used in large-scale cloud systems or data centers to distribute workload and improve reliability. The embedded OS is lightweight, efficient, and designed for specific devices like smartwatches, microwave ovens, or camera systems. It usually runs a single, focused application with real-time constraints. A network OS manages communication between multiple computers in a shared environment. Think of servers in a corporate office or school lab. It handles data sharing, device access, and user management over a network. Among all these, RTOS stands out for one reason: precision. It's an operating system with deadlines, built for scenarios where timing is not just important. It's critical. To ground our understanding, let's hear how industry giants like IBM define a real-time operating system. IBM defines it as a specialized operating system designed to handle time-sensitive tasks with precise timing constraints, ensuring predictability and stability. In simple terms, an RTOS is built not just to work fast, but to work on time, every time. It's used in places where delays aren't just inconvenient, they're unacceptable. Imagine a robotic arm performing a delicate surgery. If a task is late by even a millisecond, it's not just a bug, it could mean disaster. Now let's understand insider things of a RTOS. Imagine the CPU is ready to execute a task, but what exactly is in a task? Each task comes with its own context, like a saved workspace. This includes the stack pointer, which holds local variables, return addresses, and function call data. Working registers, which are general-purpose CPU registers used during execution. The status register, which stores critical flags like 0, carry, interrupt status, and more. And the program counter, which tracks where to resume when the task runs again. These elements allow the CPU to pause one task, switch to another, and return later without losing progress, like hitting pause on one app while switching to another. Now, who decides which task runs and when? That's the job of the scheduler, the core logic of task management. In some systems, it's event-driven. Tasks are triggered by external events or interrupts. In others, it's time sharing. Each task gets a fixed slice of time, like a rotating spotlight. No matter the method, the scheduler ensures one thing, that every task gets its time, precisely, predictably, and without missing a beat. Still confused? Now let's take a real-world example. Here is a robotic arm performing surgery. Precision, timing, and coordination matter more than anything. Behind the scenes, the RTOS juggles 6 critical tasks. Motion control, for accurate movement. Sensor feedback, constantly checking position and force. Vision processing, interpreting camera input in real time. Safety monitor, ready to halt everything if something goes wrong. Communication, talking to the surgeon's console. And GUI, for status updates and controls. Each of these tasks needs to execute at the right time, with the right priority, and the RTOS handles it effortlessly. But what if something unexpected happens? Suppose the system is busy reading sensor feedback, and suddenly a motor fault is detected. The RTOS doesn't panic. It immediately halts the current task and jumps into action, executing a special emergency routine called an ISR, Interrupt Service Routine. The ISR handles the fault, logs it, maybe shuts down the motor, whatever's needed to ensure safety. Once it's done, the RTOS doesn't skip a beat. It calmly returns right back to where it left off in the sensor task. That's the power of real-time responsiveness. Now let's see what are the RTOS features. Determinism. An RTOS doesn't just run fast, it runs predictably fast. Every task is executed within a guaranteed time window. Priority-based scheduling. If a task is life-critical, like a heart rate monitor, it gets a direct access to the CPU. Multitasking. An RTOS can handle several tasks at once without breaking a rhythm. Interrupt handling. Emergencies occurs, the RTOS listens, jumps to action, and handles interrupts instantly. Task synchronization. When tasks need to share data or resources, the RTOS makes sure they cooperate, no collisions. Minimal latency. Time matters. An RTOS reacts in microseconds. Memory management. Every task gets its own space. The RTOS allocates memory smartly to prevent overlap and crashes. Resource allocation. Whether it's sensor time, buffer space, or a communication bus, the RTOS decides who gets what and when to keep the system flowing smoothly. If you see, in the world of real-time operating systems, you've got options, from open-source favorites to powerful commercial solutions. FreeRTOS, Zephyr, ThreadX, VxWorks, and more, each with its strengths suited for different needs. But if you're getting started, FreeRTOS is often the go-to. It's lightweight, well-documented, actively maintained, and widely supported across microcontrollers. So let's enter to the FreeRTOS. FreeRTOS lightweight, open source, and designed specifically for embedded systems. Despite its tiny footprint, it's powerful enough to run on countless microcontrollers. Alright, enough with the theory, let's bring it to life. We're going to build a FreeRTOS-based application. In this application, we will use a 9-axis motion sensor and a simple buzzer, all running on the PSoC 6 Pioneer kit. Now let's see the interface. Here we have connected our BMX160 sensor to PSoC 6 Pioneer kit via I2C lines, SDA and SCL, and providing 5 volts as a VCC input volt with ground connection. On the other hand, we have a buzzer. We connected positive side of the buzzer to GPIO pin and negative side to ground. So, here we've defined 2 tasks. Sensor task to read motion data from the BMX160 sensor with the stack size of 1024 with the priority of 2, and buzzer task to control the buzzer output with the stack size of 5 and 12 with the priority of 1. Did you notice the priorities? The sensor task has a higher priority than the buzzer. That means the scheduler will always favor it when both are ready to run, ensuring sensor data is read consistently while the buzzer runs in the background. Now, vtask start scheduler. This is the turning point. The moment this line runs, FreeRTOS takes full control of the CPU. From here on, all task switching, timing, and execution are managed entirely by the scheduler. Your main function steps aside, and the RTOS takes the wheel. Now let's dive into the sensor task, the core of our application logic. The first step here is I2C initialization. I2C is a serial communication protocol that allows the PSoC kit to talk to external devices, in this case, the BMX160 sensor. We set up the SDA and SCL pins, configured the I2C bus frequency, and we're ready to communicate. According to the datasheet, the default I2C address of the BMX160 is 0x68. It means when we send or request data, we're addressing device 0x68 on the bus. Now, to verify that our sensor is alive and communicating, we first try to read its chip ID. As per the datasheet, the chip ID is stored at register address 0x00. If we read back the value 0xD8, that confirms our sensor is responding correctly. Once the sensor is initialized and verified, we use this function to read all the raw motion data, accelerometer, gyroscope, and magnetometer in one go. This helps us collect real-time motion insights, which we will calibrate into meaningful physical units next. Look at the terminal. This output gives us real-time insight into motion and orientation. These values represent acceleration in G's gravities, angular velocity in dps degrees per second, and magnetic field strength in microtesla. Watch it carefully. Now, our second task is even simpler. It toggles a GPIO pin to turn the buzzer on and off every 500 milliseconds. This gives us a periodic beep, an audible confirmation that this task is alive and executing. And since this task has a lower priority than the sensor task, it runs only when the sensor task is idle, a perfect demonstration of preemptive multitasking in action. So in just a few lines of code, we've implemented multitasking, priority scheduling, real-time sensor reading, all running on FreeRTOS. Remember, in this video, we only focused on the main.c file, the heart of the logic. If you're curious about the full setup, from cloning the libraries, understanding middleware structure, to creating a modest toolbox project, just drop a comment below. We'll capture everything and create a step-by-step video just for that. Until then, keep tinkering, keep learning, and stay real-time. If this helped you understand FreeRTOS a little better, hit that subscribe button. See you in a next Embedded T video.